Hey guys, thanks for joining this video lecture for, I think it's meant for Wednesday, March 20th. And again, sorry for being gone for the science conference and whatnot, but, I think that's overall a good thing for all of us and for Waynesburg, just to let the rest of the world know we exist and that we do some interesting research with our undergraduate research students. So anyway, here, remember last time we talked about the formation of imine and the hydrolysis of imine. And the formation of imine happens with, let me see, the primary amine and a carbonyl, a ketone, or aldehyde that gets you to the imine. But of course, a good question would be what happens if you have a secondary amine, because this is a secondary amine here, right? And it's secondary because nitrogen is attached to two carbons. So what happens, the long story short, is that you do get an enamine. And that's a fact that I don't think you should try to memorize. Anytime you rely on memorization, you will waste time, but you're really not helping yourself, because you're not really connecting this material with anything else we've learned. So you kind of have to learn each thing in its isolation, and it just takes more time to understand the whole thing, and it's going to be really easy for you to forget everything. So let's think about why it is that you get enamine. Instead of memorizing, one of the really kind of helpful things to do when you're learning a new reaction is to kind of notice something that you already know that's similar to this, and then I want you to recognize how it might be similar to enol. Okay, right, this was enol, and it's called enol because you got alkene, right, and oxygen all on the same carbons. So enamine is the same thing. You got alkene and amine on the same carbons, so it's an enamine. And I put the red dot on the same carbon. I want you to notice those are the same carbons. And so the best way to understand this reaction, of course, is to think about the mechanism. So let's think about that. And it's really the same story. Just because we went from primary to secondary, I mean, the nature of the reaction is not going to change much, you'll notice. And if you, of course, use a tosic acid, right, that's tosic acid. Maybe we'll actually write that. It's a strong acid, so it's gonna protonate the carbonyl. And what happens next? Well, you get the protonated ketone, of course, and that can be intercepted by the amine, right, in a nucleophilic addition reaction, which will give us the tetrahedral intermediate, like so. This extra proton, remember, it can always hop around between different heteroatoms. That phenomenon is called rapid proton transfer. That is something that is constantly happening back and forth, whether we like it or not. Which means that sometimes that extra proton is on this oxygen, and at that moment that's being susceptible to being pushed off by the extra lone pair of nitrogen. And once that happens, by the way, I want you to notice up until this point, the mechanism is essentially identical to the imine formation. And in fact, you get basically an amine, except this is positively charged, and the carbocation, not carbocation, the positive charge cannot be gotten rid of easily by doing something to the nitrogen directly, because there's no proton on the nitrogen to take off. Anyway, this is called, if you recall, an iminium ion. Iminium ion or cation. One way you could resolve this positive charge would be that if you do an E1 reaction to remove the proton alpha to it or next to it. So this is technically like an E1 reaction. And the product of an E1 reaction, of course, is an alkene, and that's what you get. So that's enamine. Okay. So the reason why you get that alkene component in an enamine formation is because that's the only way to resolve the positive charge on the iminium ion. So by necessity, secondary amine would give you enamine as a neutral species instead of imine. Okay. So this would be a good time to pause the video and see if you could predict the product or the study material in this case, and the product here. Okay. So I want you to notice here that the secondary amine would have been this, and this is the carbon that would have had the carbonyl, and there would have been a hydrogen here instead in the study material. So all of that to say, the study material must have been this amine, secondary amine, and this aldehyde. Okay. And again, it would be a really great study for you to come up with the mechanism for this reaction on your own. Now, because the hydrolysis of imine is a thing, right? Hydrolysis of enamine is also a thing, and this would be a really important thing to figure out, come up with a step-by-step mechanism on your own. We won't do that step-by-step here per se, just because it would be pretty redundant with the imine hydrolysis, but I could at least show you the beginning step, right? And that is, again, protonation, but the protonation can happen like this. You could protonate the nitrogen directly for sure, but if you protonate the carbon, the enamine carbon, you would get this iminium cation species that is resonance stabilized, right? And that of course makes this carbon right here very electrophilic, and so the opposite of what we did earlier, instead of kicking off water can attack that right here. Right, and so maybe I'll just at least write that in. And eventually what you would get after the iminium cation hydrolyzes is that ketone and the secondary amine. All right. If you have questions about any of these, of course, please write them down or something like that, and feel free to ask on Friday when I'm there in person. This would be a good time if I was there in person, like, I would ask, do you have any questions? But moving on, this Wolff-Kishner reduction is really useful. It's not quite like any of the reactions we've talked about, where you can reduce the ketone all the way to alkanes, not just to alcohol. And the way you do that is with hydrazine, which is this compound here. It's essentially like a very juiced up version of, it's like an ammonia on steroid in terms of nucleophilicity, because two nitrogens that are nucleophilic are attached to each other, sort of upping the electron density of both. So it's a very strong nucleophile. And so the beginning part of this is exactly like the imine chemistry. And in fact, it's really not going to be different. But you notice, like, I'm not showing any acid catalyst. Part of that is because hydrazine is a strong nucleophile, which could attack or nucleophilically add to the ketone, no problem. And we could have rapid proton transfer to neutralize this. And now we are here, and so that nitrogen, which is very electron rich, could kick this off. Now, some of you might feel a little uneasy about kicking off hydroxide because hydroxide is not the best leaving group per se. It is a leaving group, it's just not a good one. But the reason why this does kind of happen, part of it is because of the heat that we are adding. Remember, heat tends to encourage elimination type reactions, such as this we just eliminated hydroxide. And plus, the eliminated hydroxide is able to pretty much immediately become stable water by picking up that extra electron anyway. And that's part of the reason that this happens readily. Now I'm writing another hydroxide because that is something we're adding as another reagent. But at this point, you basically essentially made an imine. By the way, there is a word for this. It's called hydrazone. It's an imine that's made of hydrazine. It's called hydrazone. Okay. Now, this has proton that could come off in the presence of a strong base like hydroxide. And you could have this amide anion, which has this resonance form. This is not a reaction, but it's resonance. And hopefully you could tell like where we're going with this, because now that carbanion could pick up a proton and essentially reduces that carbon there. It gains a hydrogen overall, right? So I'm just gonna draw this with like a irreversible arrow because carbanion is very basic, so that would not be a very reversible reaction. That gets us here, and remember we still generated more hydroxide, so this is abundantly available that could take off somewhat acidic proton like proton on a heteroatom. that would leave behind negative charge on the nitrogen. And hopefully you could kind of tell where we're going with this, because if this collapses, you could make triple bond between the two nitrogens, leaving behind a pair of electrons to make this carbanion. And you just created a very stable nitrogen gas, which evolves, right? And then if this picks up a proton irreversibly, that's your product. Okay. So that's how Wolff-Kishner reduction works. Here's an interesting problem. Predict the reaction kind of a problem. So if you treat this natural product from pine trees and cedar trees, alpha pinene, it's got that foresty woodsy smell to it, is given by these small compounds given off of the trees. Anyway, if you treat this with ozonolysis and then Wolff-Kishner reduction, what is the product that you would get? This is the kind of stuff people had to do in the olden days to figure out the structure of a complex natural product. They would degrade the natural product with known reactions and then make something simpler, which maybe they could identify, or maybe they have a standard for that simplified molecule, and then they reduce what the original structure must have been and that kind of stuff. Okay, so maybe give it a pause and think about the product you get. So if you treat this under ozonolysis condition, remember that cuts the double bond essentially like so. So you should get this aldehyde and this ketone. Hopefully that makes sense. If we want to keep track of the carbons, that's that carbon, that's that carbon. Now, if we were to treat this with excess hydrazine under strongly basic condition and heat it, each of those carbonyls should get reduced. This is that carbon. This is that same carbon, which if we were to draw this a little differently, you get this simple product, and that's part of the ways they could figure out the structure of something like this. Okay. Moving on, the excuse me, the sort of the another type of reactions you can expect to observe with carbonyl compounds like aldehydes and ketones is, of course, when the nucleophiles are something else other than like nitrogen or oxygen, which was the case with acetal formation, right? Acetal formation nucleophile is oxygen. Okay. With imine, the nucleophile is nitrogen. So what happens if you have a carbon or hydrogen type of nucleophiles that adds to the electrophilic carbonyl? So that's kind of the idea here. And most of these, actually all of these we've already discussed in the past, so we'll just review these really quick. This would be a really good time to pause the video to see if you could fill in the blank for everything on this page. You should be able to. So give it a pause, see if you can fill in the blanks. Okay. All right. If you were to treat this ketone aldehyde mix, ketone and aldehyde mix, with sodium borohydride, what would happen? Well, it kind of depends on how many equivalents of sodium borohydride you've got, but if you only have one equivalent, I hope it makes sense to you that the first carbonyl that reacts is going to be the aldehyde. Remember, aldehyde is more reactive than ketone, so that's what we would expect. But if you have excess, then both ketone and the aldehyde would react. So that's what you would expect. Okay. So that's with a hydrogen nucleophile, but what happens if you have a carbon nucleophile like Grignard? Right, that's something we also discussed before, and just like you might expect, if you only had one equivalent of the Grignard, the most reactive carbonyl will be the aldehyde. So you could actually do regioselective reaction here. And of course, the aldehyde carbon is flat, so that ethyl Grignard could add from either the top or the bottom face. So I'm drawing the racemic bond there, and I want you to notice that's the new bond we just formed. Okay, this is with one equivalent of ethyl magnesium chloride. If you have two equivalents, because you could add to both carbonyls. By the way, as a side note, this is just the acid workup to protonate the alkoxide that will be formed. Okay. What happens if you have cyanohydrin? Remember, cyanohydrin can be formed from the corresponding aldehyde or ketone. In this case, this would have been the carbon that was aldehyde, which apparently has a hydrogen attached to it. So I hope it makes sense to you that this would have started with the aldehyde, like that. Okay, and that would get you this cyanohydrin. And the reason why you might want to make cyanohydrin is because it gives you this new carbon-carbon bond that could be taken advantage of to make a new scaffold, new structure. For instance, we could either hydrolyze it with strong acid and heat, or we could reduce it with strongly reducing reagent like lithium aluminum hydride. And I want to show you the end result here just to show you the synthetic utility of cyanohydrin, or I guess I should say the cyano or nitrile group. So I want you to kind of know the results of these reactions right now, but as far as the mechanisms go, I'll refer those to chapter 21 when we get there. Okay, so the result is going to be this. If you reduce it, and I want you to notice how this is that carbon right there. What if you do the hydrolysis, right? So this is reduction. This would be hydrolysis. Hydrolysis is so called because by adding water, you're breaking up the carbon-nitrogen bond. And what you can actually make is this carboxylic acid. as we said, we'll discuss the mechanisms for these in chapter 21. Okay, so thank you for watching, and I'll see you on Friday for our class now.